I have a background in graphic design and teaching, and it was really important to me that the figures be beautiful and also really communicate clearly the messages that we had. The way that I check visualizations is if I can't figure out what this visualization is trying to communicate in 10 seconds, it's probably has a disproportionate noise to signal ratio. If I can't explain the chart in 5 words or less, I know that I don't know what my signal is just yet. Sometimes we as human beings have assumptions of what colors can mean. Typically, we as human beings associate colors of the sky and the ground. So, like if we're thinking like browns, greens, and blues as good, the things that are like yellow, orange, and red, we can interpret as bad. I'm going to give you what I think is the most useful resource beyond this breakdown. I'm Dr. Vanessa Rosa. I will be your guide through data visualization for today. What gives me the gall to be here before you? I have a doctorate in chemistry. I did the whole bachelor's, master's, PhD. My doctorate work, so my dissertation, was about how do we bring in 3 different fields? And so the 3 fields are chemistry as a discipline, chemistry education research, and then cognitive psychology through the lens of critical theory and statistical analysis to understand what are we doing on a systemic level to our students who want to be doctors, nurses, and any other career field that can come out of undergraduate chemistry. And how is the way that we are assessing them? Is it measuring their learning? Is it serving as a barrier? And to whom? So my dissertation work focused entirely on that. In that beautiful line of work, I've had the privilege to publish, I think, like over 10 peer-reviewed articles. And each of them, it was very important to me that the visuals be like chef's kiss. That's because I have a background in graphic design and teaching, and it was really important to me that the figures be beautiful and also really communicate clearly the messages that we had with that work. I felt entrusted with the data by students, and so it was important to me that their data get heard and represented appropriately. This is the improvement that we have made so far on our bar chart. So label what A and B represent and which technique they represent. Are there more labels that needed to fulfill that revision? So we're going to move to Savannah's, describing what the data is representing on each axis instead of X and Y. Love that suggestion. What should we put for Y? Average toxicity percent, average toxicity with a unit of measure. Love that. The number one feedback we got is that the title and axes are not descriptive. So I would say that the axes are descriptive. What title should we give this representation? Environmental scientists, chemists, ecologists. All right, so it sounds like our audience are other scientists. So no units are provided. I think we've sufficiently addressed that. Let's check though. So we've got cell viability here, technique. Yeah, that about sums it up. Techniques aren't labeled. Definitely have addressed that. And inappropriate representation used. I'm really excited to talk about this one. I'm hoping people have strong opinions about this. So I'm just going to be quiet and invite you, for the 5 of you who wrote in your pre-survey that this is the wrong representation for these data, please say more.
There's a better choice of style, maybe a pie chart. Great. What I would interpret that maybe as is that to me, the fact that it's average toxicity, the unit being percent cell viability means the bigger bar is more healthy, more live cells. So if you're saying that it's toxicity, but the lower number is more toxic, that seems like a very confusing way to present the data.
Pie charts are really useful when you're communicating parts of a whole. So what that looks like is you have one overall group on which these other categorical variables belong. So we could say the pie chart represents everybody who's attending our workshop. And within that subgroup, how many of us are wearing black shirts versus wearing other color shirts? That would be our pie chart because we're distributing a categorical variable under a subgroup. Where a bar chart comes in handy is when you're comparing a frequency count within categorical variables against one another. So then what that would look like is we want to compare how many people in CSN tend to wear black shirts and how many people in CSN tend to wear other color shirts. How does that compare to the people in Monet, like the Center for Molecularly Optimized Networks? And now it's not parts of a whole because you're comparing beyond the overall group. Where it gets tricky is averages are a measure of central tendency. And so if you think of a temperature in chemistry, that is the average kinetic energy of your molecules, that is a distribution, and you're summarizing it with an average. The problem in research data is if you're taking and reducing things down and putting it in a chart, it doesn't give people context for, are there outliers in this data set? Are there a few of these syntheses that are particularly toxic, like really bad, but there's so many that are less in toxicity that have higher cell viability that it evens it out in the average? And now you can't see that data, so it obscures it. There's also a discussion that we can have about median versus mean. So my experience, whenever you're reporting a continuous variable, your medians tend to be more accurate, more sensitive, more precise to these issues with like outliers and other problems that can happen that are get obscured by the mean. So all of that to say, I agree with the five of you who wrote that the inappropriate representation has been used. And this experience gives me a really good sense of where we're all at in communicating data visualizations. So let's just summarize really quick. We made a few fixes here. We added titles and axes, we added units. We've discussed about the viability of the data, what it means. We talked about like what Miriam brought up, the toxicity scores, and how does that translate into something as toxic? Because if something is toxic in this context, it means that it has very low number of cells that are being killed, which means that all cells are more viable. So now you're considering all of these different variables in conjunction. So in this case, AI defined toxicity as a measure of when they exposed cells to these nanoparticles, what percentage of them were viable versus not. So 0 indicates that there's no toxic effect, so all cells are viable, and 100 means that they're completely toxic, so all the cells are dead. So like Miriam said, the higher the toxicity score, the more like cell death is occurring. It's one of those measures where we've taken data and then we've divided it amongst itself. And now we're taking the average of that, and now we're just reporting the average. So if you can see, we're reducing the quality of the data at each of those stages. I look at data representations under three primary categories. The first thing I look for is, what is our signal? I don't know how many of you are, can you show me with like emojis or typing like X or 0 in the chat if you have heard of signal to noise ratios in science communication? Can you drop an X for me in the chat? Okay, so we have heard overall of this signal to noise phenomenon. I put real examples of charts, if you can believe it. It's from a website called WTF Visualizations, which of course WTF stands for what the frick. But if you click on this link, it'll take you to a real visualization that was published in some means. Some of these are from blogs, some are actually from articles. And I like them because it highlights each of these specific issues. So if we're looking at this one, the signal to noise ratio on this chart, would you say it's more signal or more noise? Meaning, signal is the clear message it is trying to communicate, and noise is all the other potential interpretations of what the chart could be communicating. So for me, the way that I kind of gut check visualizations is if I can't figure out what this visualization is trying to communicate in 10 seconds, it's probably has a disproportionate noise to signal ratio. To me, this visual is particularly noisy. We've got the residues number, which I'm not totally sure why that matters in the context of it, but they differ from the numbers that are listed on the bottom. And then on the left axes, we have two different measures. We have some markation of like negative values that are moving down and some that are negative and moving up. There's a lot of what I think would be confusing misinterpretations of the data here. So I would consider this to be a very noisy chart. So that's the first thing that I look for. And when I'm creating the visualization, of course, that means what is it that I'm trying to say? getting really clear on that before you even start to develop your data visualization has been really helpful for me. If I can't explain the chart in 5 words or less, I know that I don't know what my signal is just yet. If we had to go back to our Q1 chart and just how do you say, describe this chart in 5 words or less, what is the signal that we're trying to communicate? What would that be? So we're trying to communicate our average toxicity by technique. So our signal, would it be, if we're comparing these two, is one more toxic than the other, according to the data? So now what this is showing is that, yes, the conventional is more toxic, meaning more cells are dying when exposed to the nanoparticles that were synthesized conventionally. So that is our signal, right? Conventional kills more cells. We've got our signal fairly on lock, I would say. We're communicating here that I think the story of the data, what the data is trying to tell us is that more cells are dying under conventional synthesis. On average, more than half are dying under conventional synthesis, where, so that's like a 50% increase. And then under here with the green synthesis, we're getting a lot less death. So if toxicity is our number one concern in terms of making these molecules or nanoparticles sustainable, then that's a fairly good argument for green synthesis. Now, of course, we can't just say green synthesis kills fewer cells because that might not be true in all cases. We're looking at just an average here. And that'll be something that we'll have to explore more. Another example that I often see, particularly amongst chemists, is an arbitrary use of color. Here, for example, in this visualization, they just decided to give every single year a different color. We as human beings tend to group things by color. So there may be some sort of confusion or underlying assumption that all of the columns that are blue are somehow meaningful, and all the ones that can be grouped in green might be meaningful. Unless you can think of an actual reason why you need to change the color of every single data point, it could just be noise. And then the last one here is just competing visual elements. You'll see this a lot in chemistry papers where they'll overlap their own chart and just don't like let the people see the data. We want to see the data. We want to know what happened to FDS55. Like we don't even know what was happening back there because it's hidden. So once you're very clear, like you can summarize the story of the data in 5 words or less for the visual you're trying to create, you have your signal. Your goal is to protect it, to avoid any noise that can take away from that. So a complex one is like what I mentioned earlier. I try to give you the three most common. And then in the pre-survey data, I asked you to set your own confidence of your ability, distinguishing kind of the basic issues with data visualization from things that can be more complex and nuanced. So try to give you a complex one too, so that you could get that skill set. A complex one can be color bias. So here we can say, oh, favorable, green is good, and then, oh, yellow is sad, no yellow or red. So just be cautious as to how you're coloring items. Sometimes I've seen where the intention for the scientist was to assign an arbitrary color that had high contrast to the other color. Sometimes we as human beings have assumptions of what colors can mean. And so to be cautious with that. Typically, we as human beings associate colors of the sky and the ground. So if we're thinking like browns, greens, and blues as good, as favorable, and things that are more colorful, toxic, venomous vibes, so things that are like yellow, orange, and red, we can interpret as bad. So just be cautious with that because we might not have those associations, especially since we pride ourselves on being so objective, but other people could have those associations. I'm going to give you what I think is the most useful resource beyond this breakdown, and it falls within the category of representation. We talked a little bit about pie chart, bar chart. What are we supposed to use here to communicate averages or distributions of data? I gave you an example of a chart that models each of these three pitfalls and, of course, our complex one. But let's go to this visualization software. And I'm going to put it in the chat just so that you can check out how cool this thing is. So when I was trying to create a visual summary of which representations I tend to gravitate towards in different contexts, this is the one that I found that I thought was the most useful. So it asks you, what kind of data do you have? Pick the main type. So you have to think about the one that stands out the most using the buttons below, and then let the decision tree guide your graphic possibilities. So if we go back to our example, we have two types of data here. We have our categories that we've shown on the x-axis, and then we have a continuous variable here with the average toxicity. Which of those two do you think are the main type, like the one that really underscores the visual? In other words, what's the main data you were trying to communicate, the toxicity or the category? It's a challenging one because if you remove the variable, is the data still meaningful on its own? It's a good way to think about it. So if we remove the categories, now we're just talking average toxicity. If we remove the toxicity, now we're just like counting how many different labs use these different techniques. So now we have to go back to our signal, right? We've got our 5 words that the green synthesis, and I think this is why category was selected by Bell. It starts with green synthesis. Like we're trying to communicate which of the categories are more clearly less toxic, but you can't establish that without the toxicity. So I think it's very valid for this to be confusing. What I would say is when we're going with name, I would go with what can you not communicate a data point without. So you can say the frequency count of the different category types, but for toxicity, that's what we need to be able to communicate and compare about, other than just category establishment. So I would go with numeric on this one, but if you wanted to go categoric, you could as well. So if we're doing numeric, do we have 1, 2, 3 or more numeric variables in our chart? So how many numeric variables do we have? We've got one numerical variable here, so we're going to follow this down. And what you'll notice is that we can have a histogram, but it's going to show you the distribution. So what this would look like is that you'd have percentages listed on the x-axis from like 0 to 100%, and it would show you frequency counts of how many of these different techniques were on there. Or you could have a density plot. What I would actually do for this data, and this is where it's like nothing is a perfect science, right? I highly value when we're looking at measures of central tendency like averages or medians, box plots, and I'll explain why. So this is the data visual that I made for our research question 1 comparing the two. This is what's known as a violin plot and a box plot and a dot plot. So I might be messing with my noise here a little bit. But basically what it shows is that every single one of these dots is a data point. And that data point has its toxicity score, same percentages as earlier. And what the box plot shows is that it gives you the first quartile. So like this is the 25th percentile of the data. This is your median, and this is your third quartile. And everything that's outside of it is a bit of an outlier in terms of that standard deviation for the measure. You get to see these for green synthesis and conventional synthesis. So before we just got a bar chart that basically showed this filled in all the way down compared to that filled in all the way down. Here we actually get to see that even in its bottom 25th percentile of toxicity, conventional synthesis simply cannot compete with green synthesis overall. And what I love about Flourish is that it gives you interactive possibilities too. So if you wanted to click around yourself and not have it mediated by me, you could. What I value about this is that you can check, like for carbon nanotubes, is it still valid to say that green synthesis is more favorable? How about gold nanoparticles, for which we only have one sample size here, so we have to be careful about saying that. Graphene oxide. Now we have bimodal distributions because we only have two data points. So it means that if we just reported this average, we're just caught in the middle of these two data points. And that could be a very biased representation. So this one I feel like more fully tells the story of the data that was hidden behind the bar chart of the averages. And you can see that I've tried to give you the main point with the title. That's a practice that I like to try to use. Like, why does this matter? Green synthesis reduces nanomaterial toxicity by this percentage. And then I gave a little context for it. Context is an important measure. That's going to be the third category that you can use to evaluate representations. And I would love to ask that you please complete this post-workshop survey so that I can evaluate the success of it. And thank you for your time.